Now let us discuss applications of Gauss law. Gauss law states that total electric flux over any closed surface is equal to 1 by epsilon naught times net charge enclosed by the surface. Gauss law equation is pi is equal to closed integral E dA cos theta is equal to 1 by epsilon naught times charge. E stands for electric field. dA is small portion, small area. Integral dA will give us total area. In case of closed surface, we are going to use closed integral. Cos theta. Theta is angle between normal to the surface and the electric field. That's equal to 1 by epsilon naught times total charge enclosed by the surface. The flux is number of lines. So it's a scalar quantity. The flux value may vary from minus, it may have minus value, or it may have plus value, or even it could be zero, the total value. The total flux in a closed surface, may be zero, or it may be positive value, or it may be negative value, because theta value may change in case of a closed surface. Okay. Imagine magnetic force lines are acting. Imagine electric force lines are acting parallel to the board. Okay. So if you imagine an area like this, okay, then this is normal to the surface, and this is electric field direction. Imagine positive charges are here. This is normal to the surface. This is electric field direction, and the pencil, this indicates normal to the surface. The pencil indicates normal to the surface. Okay, this indicates normal to the surface. Both are parallel. In case, imagine in the electric field direction, if the area is kept like this, the plate is kept like this, then electric field direction will continue in the same direction, and this will be the normal. Then theta is equal to 90 degree. Okay. For example, imagine this is electric field direction. This is electric field direction. Okay. This side positive, this side negative. You have the arrow marks is like this. Then, if the plate is kept this way, area is imagined this way, then this is normal to this is the direction of electric field. And normal is also in the same direction. Then theta is equal to 0. If theta is equal to 0 there, then pi is equal to only EA. Integral dA is equal to dA. Theta is equal to 0. In case if area is imagined like this, then also the electric field direction will be this way. Electric field will be in the same direction, and this will be the normal to the surface. Then theta will be 90 degree, cos 90 is 0. Then electric flux will be 0. In case if area is imagine like this, if it is inclined like this, then what happens? If the area is imagined this way, and this is direction of electric field, this will be the normal to the surface. This makes an angle theta. Then we take E cos theta here and E sin theta here. E sin theta acting this side. This is the direction of electric field. Then E cos theta component alone we consider. If the area is imagined this way, okay, this is the actual direction of electric field, which is not normal. Then this is divided into two components. One is E cos theta and another one is E sin theta. Okay, because this side you get opposite side, this is hypotenuse. Then this becomes E sin theta, that becomes E cos theta. This is adjacent side, that becomes cos theta. So the E cos theta factor is here. Okay, this electric field is divided into two components, E cos theta and E sin theta. We take only E cos theta. That's why we have E cos theta here. Now we have applications of Gauss law. In the applications of Gauss law, first application is electric field at a point due to infinitely long charged wire. Imagine this is a long wire. Imagine this is a long wire. Total charge in the wire Q is equal to lambda into L. Q is equal to lambda into L. Where lambda is linear charge density, L is total length of the wire. L is total length of the wire. You just imagine the total length of this wire is 7 meters. Total length of this wire is 7 meters. Cost of 1 meter wire is 10 rupees. Then total cost of the wire is 70 rupees. Cost of 1 meter wire is 10 rupees. And if the total length of the wire is 7 meters, then total cost of the wire is 7 into 10, that is lambda into L, that is 70 rupees. So in the same way, in 1 meter length, if there are 10 microcoulomb of charges, in 1 meter length, if there are 10 microcoulomb of charges, then in the total length 7 meters, total charges will be 7 into 10 microcoulomb of charges, that is 70 microcoulomb of charges. So in the same way, if lambda is linear charge density, that is charge per unit length, and L is total length of the wire, then Q, total charges in the wire, will be equal to lambda into L. Now we are going to find out the electric field at a point due to this charged wire. The wire is fully charged. Okay, we imagine a Gaussian surface in the shape of a cylinder. Imagine a Gaussian surface. If you imagine a Gaussian surface, then electric field will be acting in this direction. Normal will also act in the same direction. Electric field and normal both will be acting in the same direction. Electric field is acting in this direction. Normal to the surface. This being positively charged. So electric field will be here. At this point, electric field will be in this direction. At this point, electric field will be in this direction. At this point, electric field will be in this direction. But at all these points, if you find out a normal, it will be in the same direction. This is direction of electric field, and normal is also in the same direction. At this point, if you want electric field, this will be the direction of electric field. To that point, to that area, this is normal to the area. So wherever on the surface, curved surface, if you find out electric field and normal to the surface, both are parallel to each other. Therefore, theta is equal to 0. Cos theta is equal to cos 0. Cos 0 is 1. Whereas at the top surface and bottom surface, electric field will be acting along this direction, whereas normal to the top surface is acting in this direction, along this direction. Therefore, theta is equal to 90 degree here. The same way at the bottom also. Here electric field is acting in this direction and this is normal. Then theta is equal to 90 degree here. The same way at the bottom also, electric field is acting along this direction or this direction, and normal is acting in the downward direction. Therefore, theta is equal to 90 degree. Cos 90 is 0. The total flux for this case is equal to closed integral E dA cos theta for the curved surface plus closed integral E dA cos theta at the top surface plus closed integral E dA cos theta at the bottom area. Whereas at the top area and the bottom area, theta is equal to 90 degree, then cos 90 is equal to 0. Therefore, these two terms gets cancelled. This becomes 0. This also becomes 0 because theta is equal to 90 degree in both the cases. So total flux phi is equal to closed integral E dA cos theta only for the curved surface we get. E, electric field, and integral dA, a small area is A. If you integrate, we are going to get total curved surface area of the cylinder. For the curved surface area of the cylinder, formula is 2 pi r h. Here instead of h we use L. Height of the cylinder is equal to length of the wire. So instead of h we use L here. According to Gauss law, this is equal to 1 by epsilon naught times total charge enclosed by the surface. In this case, it is equal to lambda into L. Then E is equal to lambda divided by 2 pi epsilon r because L and L gets cancelled. Then electric field at the point E is equal to lambda divided by 2 pi epsilon naught r. This is electric field at a point due to an infinite charged wire. Then this one, electric field due to a charged plate. Electric field due to a charged plate. Imagine a charged plate like this. Imagine this is a metallic plate and which is being charged, this is being positively charged fully, and sigma is charge density, that is charge per unit area. In 1 meter square area, sigma charges are there. If A is total area of the plate, then total charge will be equal to sigma into A. Okay, in 1 meter square area, sigma charges are there. Total area is A, then total charge will be equal to sigma into A. That will give us total charge. Okay, dA is small area within this total area. dQ is charge present here. Then dQ is equal to sigma into dA. Sigma is constant, that is charge density, charge per unit area. Now imagine a metallic plate which is being positively charged. If the plate is being positively charged, then this will be the direction of electric field. Electric field direction will be this way. Electric field direction will be here. If this being positively charged at the back side also, electric field will be acting along this direction. So if I find out normal to imagine a Gaussian surface and I find out normal. Anywhere I find out normal, it will be in the same direction along with electric field. Imagine a Gaussian surface like this. Imagine a Gaussian surface like this. Imagine a Gaussian surface somewhere here. Okay, now if you look at this, the total flux phi is equal to closed integral E dA cos theta at P at this point, plus closed integral E dA cos theta at P dash, plus closed integral E dA cos theta at the curved surface area. So if you consider this as the point P here, at this point, the electric field is acting along this direction. Okay, normal to the surface is also acting in the same direction. Therefore, theta is equal to 0. At this point, both are acting in the same direction. Therefore, theta is equal to 0. Cos 0 is 1. Whereas at the curved surface area, you see that electric field is acting along this direction. And if I find out normal to the surface, the normal will be this way. And electric field is acting along this direction. Angle between normal and electric field is 90 degree. But anywhere on the curved surface area, theta is equal to 90 degree in this case. Cos 90 is 0. So electric field due to the curved surface area becomes 0. So due to this, the electric field becomes 0. Here you have E is equal to, E we just take it as electric field A, and integral dA. A is integral dA. dA is small portion in the metallic plate, in the charged plate. Integral dA, if you integrate such small areas, I'm going to get total area. So that's equal to E into A. And for this portion, P dash, again you get E into A. According to Gauss law, this will be equal to 1 by epsilon naught times total charge enclosed by the surface. Okay. Then 2EA is equal to sigma into A. Then AA gets cancelled here. Then E is equal to sigma divided by 2 epsilon naught. Actually, what is here? Here you have this is equal to 1 by epsilon naught times this is equal to 1 by epsilon naught times Q is equal to sigma into A. AA gets cancelled. Then you get E is equal to sigma by 2 epsilon naught. In case if there are two charged plates, parallel to each other, if there are two charged plates like this parallel to each other, imagine this plate is being positively charged and this plate is being negatively charged. Okay, if this plate is being positively charged, the electric field will be along this direction anywhere. And this side also electric field will be acting along this direction. If this is a negatively charged plate, the electric field direction will be along this direction. According to properties of lines of force, the force lines will terminate at negative charge. Okay, so electric field direction will be along this direction. If you have a positively charged plate and negatively charged plate like this parallel to each other, if you have one positively charged plate like this and negatively charged plate like this, okay, it should be straight to each other. So imagine that this plate is positively charged and this plate is negatively charged. and if these two plates are kept like this, okay, due to positively charged plates, the force line will be along this direction. Due to this positively charged plate, the force line will be along this direction. Due to this negatively charged plate, the force line will be acting along this direction. Due to this negatively charged plate, the force line will be acting along this direction. So if you consider outside the plate, this is direction due to this positively charged plate. This is direction due to negatively charged plate, this plate. So they are getting cancelled. At this side also, this is direction of electric field due to this positively charged plate, and this is direction of electric field due to this negatively charged plate. Therefore, they are getting cancelled. They are equal in magnitude also. And between the plates, due to this positively charged plate, this is direction of electric field, and due to this negative, this is direction of electric field. So between the plates, the electric field are in the same direction. Therefore, they are active. Just look at here. This is electric field due to positively charged plate. This is electric field due to negatively charged plate. This is electric field due to positively charged plate. This is electric field due to negatively charged plate. Okay, and they are getting cancelled. Imagine these two are the charged plates. Okay, outside the plates they are getting cancelled. Inside the plates they are added up because they are acting in the same direction. Then electric field E is equal to electric field due to positively charged plate plus electric field due to negatively charged plate. Electric field due to a single charged plate is equal to sigma by 2 epsilon naught. Therefore, sigma by 2 epsilon naught plus sigma by 2 epsilon naught, that is equal to sigma by epsilon naught. This is equation to find out electric field due to charged plates which are kept parallel, where one plate is positively charged, another plate is negatively charged. Now let us come to a sphere. Imagine this is a metallic sphere. Imagine this is a metallic sphere of radius 10 cm. Just for understanding, let us take it as 10 cm. Imagine this is a metallic sphere. This sphere is being fully charged. Okay. So on the surface, wherever I find out, this is going to be the direction of electric field. Electric field will be normal to the metallic sphere. Okay. For example, if you imagine a small area dA, and to that area, this is direction of electric field, that is direction of electric field. Even normal will also be in the same direction. Wherever I find out, this will be the normal, and that will be the direction of electric field also. So for a small area dA, this is direction of electric field, and the same is the direction of normal. Therefore, theta is equal to 0. Now, let us imagine a Gaussian surface, a sphere of radius 20 centimeter. Okay, and let us imagine one more Gaussian surface of radius 5 centimeter. This is a metallic sphere with a 10 centimeter radius. Let us imagine a Gaussian surface sphere with 5 centimeter radius inside the sphere. Let us imagine another Gaussian surface sphere of radius 20 centimeter outside the sphere. It's like this. All the three spheres have common center. They are concentric spheres. They have common center. So in that case, if the metallic sphere is kept like this, on the metallic sphere there are positive charges are there. Okay, inside the metallic sphere there is no charge, which is where this radius is R1 equal to 5 centimeter. This radius is 5 centimeter. This is only 5 centimeter. Let us imagine this is 5 centimeter. This is 5 centimeter. Okay, and this is just 5 centimeter, and R2 is equal to 10 centimeter. Okay, this is R2 is equal to 10 centimeter. This is 5 centimeter. Okay, this R1 is 5 centimeter, which is inside the sphere. Radius of this sphere is 10 centimeter. Outside the sphere, you just imagine radius of this biggest sphere is 20 centimeter. Imagine this is a metallic sphere, and this metallic sphere is being positively charged. This sphere is being positively charged. Okay, the sphere which is inside Gaussian surface, it has no charge. Therefore, if you apply this equation, Q becomes 0. Pi is equal to closed integral E dA cos theta, that is equal to 1 by epsilon naught times total charge enclosed by the surface. Okay, and we have E, and integral dA is equal to total area A, and here theta is equal to 0 because electric field and normal are parallel to each other. Theta is equal to 0. Then cos theta is equal to cos 0, that is equal to 1. This term becomes 1. Then total charge Q, total charge is Q. Area of a sphere is 4 pi r square. volume of a sphere is 4 by 3 pi r cube. Area of the sphere is 4 pi r square. So instead of A we substitute 4 pi r square. So E is equal to Q divided by 4 pi epsilon r square. E is equal to Q divided by 4 pi epsilon r square. In case if this is capital R, where R is the radius of the sphere, where R is radius of the sphere, it has its value, charges are there, then we get E is equal to Q divided by 4 pi epsilon naught capital R square. If it is a small R1, where Gaussian surface is inside the sphere, then you get R1 square here, but cube becomes 0 because there is no charge enclosed within the surface, then electric field will be 0. So electric field inside the charged sphere will be equal to 0 because Q becomes 0. Because according to Gauss law, total electric flux phi is equal to 1 by epsilon naught times total charge enclosed by the surface. If you imagine a Gaussian sphere inside, there is no charge enclosed within this, therefore Q is equal to 0, therefore electric field is 0. And if you imagine a bigger sphere of 20 centimeter radius, that is R2, then it becomes R2, then it has charge, because for this imaginary bigger sphere Gaussian surface also, these charges are within the surface, therefore total charge is Q is there, but here we have to use R1 square, R2 square for this, here for this one R1 square, whereas for the metallic sphere we have to use capital R. So this is the applications of Gauss law. Hope you understand. Thank you.